Let's see if this works now. So I've already made this recording once, but it had no audio. So since I've already written everything out, I am just going to try to save time and narrate over this. You should see the bouncing red dot, so follow that along. Here we go. So there's a warm up here. It would be good if you paused this video and tried this problem and ignored what was written down below. So pause now and try it for yourself if you want the full classroom experience. Okay, here we go. Problem number one. You're supposed to find a formula for this. It is 1 plus 2 plus 3 all the way up to n. We've already done this in class. We did it one way. So this is our formula, n times n plus 1 over 2. One way that we did it in class, this was a few months ago, we wrote out the sequence forward and backwards and then paired everything up, and then we divided that answer by 2, and that is how we ended up with this formula. Another way is we build it with blocks. So you have a staircase, and you have this would be like your n, and then plus this 1, and then width would be n, so it would be n times n plus 1, but we only want half of that because this is our sequence. It goes 1, 2, 3. That's what our 1, 2, 3. We don't need both of these staircases, so that's why we divide by 2. Maybe that looks familiar to you now. So, moral of the story is we have a sequence, and its sum has a formula. And that's what we're building to this. We're going to be proving formulas in a different way than visual like this, called the method by induction. Okay, so number 3, you're supposed to write out the first 10 numbers of the Fibonacci sequence. 1, 2, 3, 4, 5, 6. I just wrote out the first 7. Sorry, I stopped at 7. So that's the Fibonacci sequence. If you've never seen the sequence before, you get the next number by adding the previous 2. So 1 plus 2 is 2. Or sorry, 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8, etc. Then, if you were to take these, this is our first term. If you were to plug in 1, now there's not supposed to be blue rectangles on this. I don't know what happened here. If you were to plug in 1 to this formula, even though this formula contains square roots, it would still give you back the number 1. And if you put in the number 2 for the second term, you're also going to get 1 out. If you put in the number 3, you're going to get out 2. If you put in the number 4 up here for n, you're going to get out the number 3. And so no matter what integer you put in here, you're going to get out an integer, and it generates the Fibonacci sequence. So the moral of this story is that we have a series here, a sequence of numbers here, which generates the Fibonacci sequence, and the Fibonacci sequence has a formula, which is super, super cool. Plus, if you do 1 plus the square root of 5 over 2, we talked about this in class, 1 plus the square root of 5 over 2 is approximately 1.61 something. It is the golden ratio. So buried inside of the Fibonacci sequence is the golden ratio. We spent a little bit of time in class talking about the golden ratio and its connection to Fibonacci sequence, but I'm going to cut that here. So the moral of the story is that sequence has a formula. We could prove this formula using induction. It is a little harder. It's quite a bit harder than anything IB will require you to do, and we're actually not going to do it in class. So if you want to do it for fun, let me know. I have actually done it for fun myself, because that's how I roll. Math is fun. Okay, let's move on. So, in general, we have all of these steps here. I'll kind of summarize it for proof by induction. You start by proving that the first term is true, and the formula works for the first term. Then you assume that it works in general, and then you prove that it'll work for every step after that. So in a sense, what your analogy I gave is the first step is like how you're getting on to the ladder or staircase, and then we can prove that no matter what step you're on or what ladder rung you're on, you can always get to the next one. Then you're guaranteed that you can climb as high as you want, and every single part of the sequence is going to work. That is the concept behind induction. I know it's a little bit different of a kind of proof. That is why it works. Then you have to write a conclusion at the end, which is a sentence that states why what you did and how you know it's true. This last part is something that IB requires. If you leave it off, you will lose points. Okay, so this is already written out. I know this is a little bit clunky, but we're trying to prove this. Let's go through this example together, and then I'm going to ask you to try some too. But of course, you can just skip ahead in the video and just watch it. So we've got the sum of odd numbers, 1 plus 3 plus 5 plus 7 plus 9 plus 11, blah, blah. And then this 2n minus 1 is guaranteed to be an odd number. It's kind of like the nth term. I can't just write n because n can be odd or even. N is counting, right? N is 1 here, n is 2 here, which is an even number, n is 3, n is 4. So this last number in the sequence has to be guaranteed to be an odd number. And here's how we do that. We say 2n. If you say 2n, you're guaranteed it's an even number because you're doubling it. And if you subtract 1 from an even number, you're guaranteed to get an odd number. So this is guaranteed to be an odd number. So that's the random place where we stop. And this example is saying that this sum of the odd integers is exactly equal to wherever you stop, that last term squared. Kind of cool, kind of interesting. Let's see if it's true. It's true. We're going to actually prove it. Okay, so the way we prove it by induction is that first step up there, we show that the first case is true. So on the left-hand side, the very first term is 1. On the right-hand side, if I plug in the first term is 1, if I plug in 1 and do 1 squared is also 1. So the right-hand side matches the left-hand side, and that means our formula works, and we can get on the staircase or ladder to start climbing. Okay, next, we assume that this whole thing is going to work for any n we choose. And that is actually the formula right there. So what you see highlighted is this thing we're trying to prove. We assume that that's true, and we prove that no matter how far I am here, I can always get to the next thing. So the next one, this is what we're trying to prove. Everything you see in green right there is also in green right here. Okay, and all of those parts are equal to n squared. But then the next term, I take this previous term, the 2n minus 1, and I'm going to figure out what the next term is when n is n plus 1. So I'm plugging in n plus 1 in red, and I'm also going to plug in n plus 1 into my formula to see if the formula holds true for when I increase n by 1. Okay, so our sequence rolls out plus the next term. It's going to equal to n plus 1 squared. And so on my left-hand side, I'm going to work on that. And again, there's not supposed to be these funky boxes. So that says 2n plus 1 equals n plus 1 squared. That's the thing we're trying to prove. I just rewrote that statement. This thing in green is the thing we get to assume. So all that collapses down to n squared on my left-hand side of the equation. But I still have plus 2n plus 1. The 2n plus 1 came from distributing the 2 and subtracting 1, so it simplifies to that. Okay, so then from there, we have this quadratic. All I did was remove parentheses here, and then factored it, so that turns into n plus 1 times n plus 1, which is the same as n squared plus 2n plus 1. And then that is squared. Hey, and that's the right-hand side. That's the thing we're trying to prove. So we did it. Okay? This one's not so bad. So anyway, so we have to write this formal statement at the end. This is step number 4 that I outlined above. Since the formula works for n equals 1, that is what we did up here, and given that it works for n, so we assumed this, it was proven that it will work for n plus 1. Therefore, it must work for all n greater than or equal to 1. Meaning we can always get to the next step no matter where we start, and I know how to start. So I can sweep out all of it, and the formula always works. Okay, this is what IB expects you to do. Oh, by the way, a shortcut for the word therefore is these 3 dots. It looks a little funky. Basically, it's just 3 dots means the word therefore. I was just trying to say ways that you could shortcut your work. We'll talk more about how to shorten this paragraph next class. IB expects you to write it all out. In the real world, outside of education, you can just end with a black box, a rectangle, and it stands for the whole place of this paragraph. But I really encourage you not to be lazy and actually write out this whole entire sentence, because you will lose points on my test, and you'll also lose points on IB if you don't include it. But if you do any work, in college or anything, they'll probably be just showing you the black box instead. Okay, next question. Way down here, what happened? All right, so I know this is down at the bottom of the page, but you want to pause right here and try this problem if you want to try it on your own. Okay, assuming you tried it on your own, here we go. We're going to go through it rapid fire. This is our left-hand side and our right-hand side. We're trying to prove that that's true. So the very first step is let n be 1. In this case, we're letting k be 1 because that's what's generating this formula, right? And so we're letting k go from 1 to 1 because n is 1. So you plug in 1 for k, and we're going to get 2 times 1 minus 1 squared, which is 1. So our left-hand side is 1. I kind of shortened some of that work right there. It's 2 minus 1. And then on the right-hand side, I do the whole formula, but I plug in 1s where the n's are, calculate it all out, and we also get 1. So the left-hand side matches the right-hand side. We've satisfied the first criteria. Next, you assume that this is true. That's our assume right here. And then you prove that it's true for when we increase by n plus 1. So let's look at this right here. This is the summation written without summation notation. We're letting k equal 1, so you plug 1 in there, you crank it all out like we did here, and you get 1. 1 squared. You plug in 2, so you go 2 times 2 is 4, minus 1 is 3, so that's going to be 3 squared. You plug in 3, and you get 3 times 2 is 6, take away 1 is 5, so you get 5 squared. And it's starting to generate that, and we end up with an odd number, 2n, like we get up to the nth thing, so I'm going to plug in n here, so 2n minus 1 squared. That's our last term. And then that equals the formula at the end. So this formula at the end, just to highlight that, is this formula right here, right? Okay. So next, that's the thing we get to assume, and you're going to be able to use that in the proof that's down below in just a minute. And then we are going to prove that this works for if I increase by 1. So this is my first original assumption, but then I need the next term. And that happens if I plug in n plus 1 in here, it simplifies to 2n plus 1. We just did that a second ago. So hopefully that makes sense. We just did that right here. Okay, when you multiply by 2 and combine like terms, you get 2n plus 1. Okay, so, and then on the other side, you also plug in n plus 1 and n plus 1. Boom, boom. Okay, all of this. Okay, so now I'm doing a 2-column proof of this. I'll try to make this fit the page a little bit better. That won't go away. I don't know why. Okay, all of this right here. Oops, not the laser pointer. All of this. I got a glitch. How annoying. No tail. Let's just do a tail. Okay. All of this right here is, I just rewrote the whole thing. So this is our entire left-hand side written right here. And all of this right here is our assumption. So to highlight that for you, all of this right here is the thing that we're assuming right there. It's the first part of what we're trying to prove. And it turns into that because that's the formula that we're given, right? And that's the thing we're assuming right there. It seems weird to do that last bit in the same color. So that's equal to this formula. And so that's what gets subbed out. So the yellow gets subbed out for the green. Okay, so, and then we still have plus our next term. And then you can just kind of work on this algebraically. Now, I wrote the right-hand side over here. You are allowed to work on both sides of the formula, but you're not allowed to cross the barrier. So when you do a two-sided thing like this, make sure you draw lines that delineate and show your reader what you're doing. Please put signs in there, lines in there, so it divides it up and makes it so much easier to read and grade. Okay, so I can change this, and I can change this. I should end up with the same equation at the end. And there's a wide variety of ways you could do the algebra on this. So follow through with my thinking here, but maybe you would have thought of slightly differently, and that's totally fine, as long as you prove that they're equal. Okay, so on this side, we do our substitution. I am viewing this right here, 4n squared minus 1. That's the difference of squares. If you're in class today, we actually talked about that too. Okay, and then this is going to be 2n minus 1 times 2n plus 1. That's the difference of squares. And then what I noticed here is that the 2n plus 1 is there and then also there. So I factored that out front, leaving me with 1/3 n, 2n minus 1, and one of these 2n plus 1s. This I distributed in. And I also, well, I took out the 1/3 out to the front, which has to triple these over here if I do that. If I take out a 3 here, it's going to turn this into a 6 and this into a 3. Again, you don't have to do it in this way, but I was just trying to avoid fractions by moving them out front. And then I distributed the n in to make it 2n squared and minus n. And then combine like terms in here, so I get 5n. And then this actually factors into n plus 1, 2n plus 3. And then I was like, that kind of looks like where I'm aiming, but I don't really want to manipulate that to be exactly this. So I'm going to mess with this now, leaving this the same and this the same. This I'm going to multiply out. So n plus 1 squared turns into n squared plus 2n plus 1. Distribute your 4 in there. Combine like terms. Get 3. Then this turns into 4n squared plus 8n plus 3. That 8 looks a little munched. And then you can factor that, and hey, those factors are the same as these factors. So we end up with the right-hand side equaling the left-hand side, and then you write your little form, your statement at the end, okay? Because the proof by induction always ends with that statement. All right, here's another one down below. It is a slightly different style. Feel free to pause and try if you want to, but you might not invent this out of thin air. So there's a reason I'm throwing example 2 in here. That's not necessarily a you try it problem. Is because there's one like it in the homework, and I've seen plenty of questions like this in the IB exam, and it's also fair game for our exam. So it's kind of a thinking differently thing, and you might not have ever thought of things this way. So let's go through this. If it's saying that we have to prove that 9 to the n minus 1 is divisible by 8. By the way, I think this is the last example here. Okay, so proving something is divisible by 8, actually this falls into the branch of math called number theory. It's not actually calculus. We'll be getting to induction involving calculus pretty soon, don't worry. So if this expression is divisible by 8, then I can say that this expression is equal to 8 times some number, as long as that number is an integer. Capital Z like this weird Z means an integer. It doesn't actually have to be a positive integer. A could be like -3 or something, right? Or -2. Because -2 would give you -16, right? If you multiply by 8, and -16 is divisible by 8. So basically, we can say A is any integer. No decimal, but any integer. So this is a different way of saying that something is divisible by 8. Now we can prove, now we have a left-hand side and a right-hand side, and I can do induction. So the left-hand side is, we start with n equal 1, and you plug in 1 there. 9 to the 1 power minus 1 is, in fact, 8. The right-hand side is definitely divisible by 8, because whatever a is, like say let a equal 1, then 8a would be 8, which is divisible by 8, and it checks out. So no matter what you pick for 8, even if it's 10, right, you'd have 80, and 80 is divisible by 8, so both numbers would be divisible by 8. All right, now you get to assume this is true. We'll come back to this comment in a second. In fact, I'll rewrite it in a second so I can explain it a little clearer. So we assume this is true, and then we have to prove for n plus 1. So everywhere there's an n, and there's only one of them, I plug in n plus 1. But it's going to be some new number that is also a multiple of 8. So I'm going to say it's going to be 8b, where b is also an integer. Same idea, it's just that this is some new number, so whatever that new number is going to be also divisible by 8, but a and b might not be the same exact number, and that's okay. All right, so let's go through this. I'm going to start with the left-hand side and arrive at this conclusion. So I'm just going to do a one-sided proof straight through. I'm going to start with this, and 9 to the n, it's a 9, not a g. 9 to the n plus 1 is the same thing as 9 to the 1 times 9 to the n. That's your exponent properties where you add exponents to get that. And then if I wanted to, I could think of this right here. This is where we're going to go back to the assumption up above. So in red, what you see right here in red, if I take this, I can add 1 to the other side. So 9 to the n is equal to 8a plus 1. That's just moving the 1 over to that side of the equation. Okay, so that expression right there is what I can plug in for 9 to the n, and you see it right there, right? All those things are equal that are highlighted in green. Okay, so if that's true, then I could distribute my 9 into there, so I get 72a plus 9 minus 1, and 9 minus 1 is 8. Well, 72 is divisible by 8, so I could factor that out, leaving me with 9a plus 1. Well, hey, 9a plus 1, a has got to be an integer. And an integer times 9 plus 1 is also an integer. So why don't we just call 9a plus 1 some random thing like b? And if you do that, you're done. You just proved that this expression is a multiple of 8. Okay, then you end up with your sentence there. Okay, so there was one more that I didn't get to in class, but that's totally cool. I hope that helps, and come on in if you need extra help.